So this is the third video in the lecture, and in this video I'm gonna tell you about, first of all, Thomson scattering. A very mouthful of a term indeed. Imagine yourself to be a kid and you are inside a room full of people, much taller than you, much broader than you, much stronger than you. You have this ball in your hand, and you, being a nasty boy that you are, you see a door outside behind the crowd, and you decide to throw the ball in its direction, hoping the ball will land outside and go away from the people, because you have something inside that ball that you don't want the other people to have. So what best you can do is you can hide it inside your pocket, but it's too big, so you have to throw it away outside, and the crowd can't move outside. It's a kind of condition for them. So what happens is, when you throw the ball, you being a kid, you don't have the energy to throw it, directly outside the gate. So you throw the ball with certain energy that you have, and the ball hits different people at different times, and the ball's chances of going outside gets lesser and lesser as time passes. But the ball has a property, it's a very interesting property, that the ball will, once launched, will not lose its energy until it goes outside. So the ball will have this very haphazard motion, when it strikes someone, when it goes past some gaps and
So it's
suddenly
like a
finds
dust
someone
particle inside a water
stopping it or
beaker.
changing its direction.
Have you
So
ever
it's
seen?
like the process of sedimentation. Take a jug of water, and you will see the dust particles following a certain way of moving through the water body. Why does this happen? Actually, it happens because the water molecules, the H2O molecules, are much, much, much smaller than the dust particle. So they strike it, around its boundary, strike dust particle around its boundary, and there's this impulse that is transferred to the dust particle. But because it is, uh, it's if affecting the dust particle from different angles, therefore the net resultant force has a unique direction, and it keeps happening over the span of time, and the dust particle follows a very haphazard motion, as you can see in the picture right now. And you can see how weird the motion is. There's so many points where the direction changes, there's so many points where the velocity changes, and because the velocity is changing, the dust particle is accelerating as well. Therefore all these influences lead to acceleration. Therefore there's this force transfer which causes the dust particle to appear as accelerating inside still water. This is called the Brownian motion. Now what I'm gonna do is juxtapose this motion and this scattering and the example of the kid earlier on with the core of a star. So let's take our own sun. What's the temperature of its core? It's humongous. It's 15 into 10 to the power 6 kelvins, which you can see in the figure. So at these high temperatures, and as per Boyle's law, the pressure is also high. So it leads to great conditions for fusion of the hydrogen atoms into helium atoms. And what comes out of the reaction are high energy gamma ray photons. So these photons are massless, and they are electromagnetic waves basically with high energy, therefore more frequency. So they have a way of moving, they move straight most of the time until they interact with something. Now they have to go from the core to the radiative zone of the star, where the Thomson scattering is more prominent, and the temperature range is around 10 to the power 6 to 10 to the power 7 Kelvin. And then it has to move through to the convective zone where the temperatures are not much high, and then to the photosphere, and then to the space, and then to the earth, and then to our eyes, and that's how we see sun. So these photons, they don't go straight inside the star, they don't have a very rectilinear motion, they have a very scattered motion. Why? Well, as we discussed in the earlier videos, the star's content is made up of ions and free electrons due to the high temperature and pressure conditions. And all these free electrons are moving here and there inside the convective zone, inside the core of the star. And the photons, being an electromagnetic wave, they have very few chances to go past all these free electrons and ions and molecules and protons and move straight away to the photosphere. It will interact with a lot of other particles in the midway, and therefore the scattering happens. So what happens that this photon is an oscillating electric field, and it has a wavelength associated with it. Now, when there is a free electron, and when this electromagnetic wave, it interacts with it, or it collides with it in the literal sense, the electric field of the electron and the electric field of the electromagnetic wave, the photons, they interact with each other. The magnetic field of the electromagnetic wave doesn't have much effect on the free electron, but the electric field has an effect. What it does, it transfers a force which, as per classical electrodynamics, is equal to F is equal to minus E into the electric field of the incoming electromagnetic wave. Now, what it does, it sets the free electron into an oscillating motion. And there is a thing to remember, and it is that the interaction between the electromagnetic wave, the incoming electromagnetic wave, and the free electron is completely elastic, because it's a low energy electromagnetic wave. Now, after having gone through much of the star, in the convection zone, it becomes a low energy electromagnetic wave. Therefore, the interaction with the free electron is purely elastic. So, the photon, the electromagnetic wave, changes direction, but it loses negligible energy in the process due to the elastic collision. So, this random walking of these photons and these interactions with these free electrons and its directions that keep changing causes it to have a delayed period of time before it reaches the surface of the sun, and that leads to Thomson's scattering. So we know that as per classical electrodynamics, the force on an electron, on a free electron, interacting with an incoming electromagnetic field is equal to the expression as you can see above. And why, you must be thinking, the magnetic field is not interacting with the electron, because the free electron is not oscillating, it's an electric field in itself, it's an electric potential. So therefore it interacts with the electric field, the electromagnetic field's electric part only. After interaction, the electron spills out the radiation due to oscillation with the same energy and with the same wavelength as the incoming electromagnetic wave, in a dipole manner, in a dipole radiation pattern, as you can see in the figure. It is a certain speciality of these free electrons that they primarily reflect off the incoming electromagnetic wave in a certain manner. And the area of cross section, which is called the Thomson cross section, is calculated as sigma t is equal to 8 pi by 3 r e square, where r is the classical electron radius. And surprisingly, the result comes out to be 6.65 barn. That means 6.65 into 10 to the power minus 29 meters, and it is independent of the incoming electromagnetic field's wavelength. Isn't it a weird answer? But that's what it is. Thomson scattering does not depend on temperature of the star. It does not depend on the pressure inside the star. It only depends on a constant, that is the radius of the electron, and therefore it is a constant. So for all the stars in the universe, including our own sun, the Thomson scattering cross section is the same, constant for all frequencies in this limit, in this classical limit. What do I mean by the classical limit? It means that the electron is not moving relativistically. That means it is not moving near or close to the speed of light. If it was, then these relations would change, considering special relativity and its results into effect. So once again I will show you the diagrams, the calculations of the Thomson's cross section. Newton's law for a charged particle and the fields of an electromagnetic wave. So what's the driving force? As you can see, when an electromagnetic wave interacts with a free electron, the primary interaction is driven by the electric field, not the magnetic field. What it does, it causes the oscillation, and the relation is given by force is equal to minus E into electric field. Now from Newton's second law, we get the relation for the acceleration, and it's inversely proportional to the mass of the electron. It suggests something, that electron scattering is dominating over the proton scattering in the plasma environment of the star. It's a very important relation. We get the power relation from the Larmor formula. The power irradiated by the free electron is given by the relation, as you can see. So this expression, as you can see, it describes the energy diverted from the incident wave of electromagnetic field by the electron's oscillatory motion. Now what we will do is that we will see the relation for intensity. Here it comes. The intensity of the incoming electromagnetic waves is given by this formula, C upon 8 pi into E square. So it is derived from classical electrodynamics and non-relativistic interactions of the electromagnetic wave with a free electron, and this is the expression for intensity. We go from here to the scattering cross section, the Thomson scattering cross section, which is our most important thing. So it's given by the ratio of these two terms that we discussed early on, the power radiated by the free electron and the intensity of the incoming electromagnetic wave, and we get this equation, we get this formula, which is basically a constant. That means The result of this ratio is a constant, and it doesn't depend on the wavelength or the energy of the incoming incident electromagnetic wave. So the Thomson constant area, cross-section area for non-relativistic uh, three electrons interactions is this 6.65 into 10 to the power minus 29. This is how it is scattered, and it's scattered in a non-isotropic manner, and the relation is proportional to cos squared theta plus 1. This ratio between the scattering cross section and the solid angle in which the electromagnetic wave is re-radiated, and for thetas equal to 0 and 180 degree for forward and backward scattering, it's more, but for theta is equal to 90 degrees, that is sideways scattering, it is less. And you can see the angular distribution also. These are some of the core assumptions of the model through which we got the relation for the Thomson scattering. The most important being the non-relativistic domain in which we are seeing things, that the particle velocity is much less than the speed of light, and the free electron, it's bound to its atom because of the high temperatures and the high pressure conditions of the plasma, the low energy of the photon due to absorption during its journey to the convection area of the star, and the momentum transfer to the electron is ignored during the interaction. So what's the application in the stellar journey of Thomson scattering? So all this random walk leads to a certain time for the light to reach the surface of the star, and for our own sun it takes around 10 to the power 5 years. A huge long time before it reaches our eyes from the surface of the sun. It just takes a mere 8 minutes. So that's how one of the largest structures in our solar system emits light. Thank you for staying with me in this lecture.